Welcome to this lecture number 6 of the course Computational Hydraulics. We are in module number 2, numerical methods, and this is unit number 2, finite difference approximation. So, what is the learning objective of this particular module? At the end of this module, at the end of this unit, student will be able to discretize the derivatives of single valued one dimensional functions using finite difference approximations. So, let us consider derivative of function, and phi is a single valued finite and continuous function of x. So, this is one dimensional function and its derivatives and function both are continuous. Phi can be approximated with point values at nodes. So, these are actually point values, individual point values for the function, and these are corresponding to nodes x0 to xn. Sometimes these are also called as grid points. These are also called as grid points. So, in this one we represent the function with discrete points. So, this is the discrete representation of function phi. So, phi can be approximated with points at nodal values. So, we have two boundary points in one dimension, and these are actually interior nodes and boundary nodes. So, at boundary points values can be specified in terms of boundary conditions, and within the interior point it should be for it should be with governing equations. So, this is the total discrete representation of the single valued function phi. Let us consider this forward difference. In forward difference, first derivative at node x naught can be calculated with limit definition. So, x naught prime can be written in terms of this limit definition, that phi x naught plus del x minus phi naught divided by del x when the limiting value of del x is tends to 0, and this can be this represents the first order derivative. Now, in this case this limit definition can be approximated, and with this approximation for finite value of delta x, we can write that phi x plus delta x minus x naught divided by del x is representing the approximated value of first derivative. So, we can apply the same approach for x1, which is interior point, xi, which is general interior point for the function, and for the points n2 n minus 2 and n minus 1. However, we cannot compute this phi prime n with this forward difference approach. Why? Because we do not have information about the point n plus 1. So, in this case we can use alternate definition of limit and we can write this phi n prime with backward difference, where this is written as xn minus delta x. So, it is moving in the backward direction. Now, if we approximate this, with the backward difference thing, again we can write for finite value of delta x, and this is representing the first order derivative. For interior points, we can approximate it using this center difference approach. In center difference approximation, we take difference of x 1 plus delta x and x 1 minus delta x divided by 2 delta x. 2 delta x is the distance between two nodes x 2 and x naught in this case. So, in general, if you write for any point I, then we can write this forward difference as delta plus xi, which is phi I plus 1 minus phi I and delta x. Backward difference I minus phi I minus 1 divided by delta x. If we use center difference, then I plus 1 minus phi I minus 1 divided by 2 delta x. This is represented in short form for the center difference, and which is the average value of this forward and backward difference. Now, if we geometrically see this forward difference, backward difference and center difference representation, then for this discretized one dimensional grid, we have distinct grid points from x naught to xn, x naught to xn, and in this case we can see that the slope between the point x1 xi minus 1 xi plus 1, that is representing the center difference, the slope which is between I minus 1 and I, that is representing the backward difference thing, and the slope between the points phi I plus 1 and I, that is representing the forward difference. So, what are the observations? Same derivative can be approximated with different forms of finite difference. Different approximations will give different results for finite value of delta x. result should converge to the same value as delta x tends to 0. This property is called as consistency of the discretization. And forward, backward and center difference approximations are consistent. However, they will not produce same value for finite delta x due to associated truncation error. Now, we will talk about this truncation error thing. Although these schemes are consistent, but there will be some difference in values. So, associated errors, one is computational error, that is round off error, computer related error, as they cannot they can store only a finite number of decimal places. Then comes this truncation error, human error due to approximation being made. So, if we consider Taylor series expansion, and this is for infinitely differentiable function, then Taylor series expansion about point xi evaluated at point xi plus delta x is represented as this form, where m equals to 1 to infinity, this is representing the higher order terms, and around xi we are expanding this. Similarly, if we take xi minus delta x, again we can expand it using Taylor series, and only difference is this minus 1 to the power m, that will determine the sign of this higher order terms. Now, approximation, forward difference approximation. So, we have approximated the forward difference using this expression. Now, if we use the Taylor series for this term, then we can write it in this format, where phi I prime is the exact value plus some higher order terms available there, and these terms all total, these are called as truncation error, and in this one the term with lowest order of this delta x is called leading error term, and this determines the order of truncation error. In this case, we can say that truncation error is of the order delta x. So, in forward difference we have exact value plus some amount of truncation error, which is of the order delta x. Now, if we see the backward difference, again we can use the Taylor series expansion, and with this one again the leading error term is having del x, which is the lowest power of delta x, and this is giving again first order error or truncation error is again of the order delta x. Now, if we repeat the same thing for center difference the result is somewhat different. In this case, in this case we are getting this term as truncation error, and you can see that leading error term is having del x square term, and in this case truncation error is of the order del x square. So, so truncation error is of the order del x square. So, in this case lower the order, more is the error. So, in this case if you have higher order truncation error, that means this approximation is more accurate compared to forward or backward difference. So, what are the observations? Forward difference approximation for phi prime x is of first order discretization, backward difference is of first order, center difference is of second order discretization, and if we take the same problem and discretize with delta x, which is equal spacing of the node points, and in this case second case if we divide it with del x by 2, distance between the grid points. So, obviously this second grid is much more finer. So, if we compare the error between this one and the second one, then we can see if we reduce the size of the grid, then your del x in case of forward or backward difference the error will be half, but in case of center difference it will be 1/4, because we have square term present there. So, higher order discretization of the first order derivative. So, we have seen that forward difference and backward difference is giving first order discretization. So, if we associate one extra point on same side, maybe this is on the backward direction, we have phi I minus 1, phi I minus 2 with associated coefficients alpha I minus 2, alpha I minus 1, alpha I. Then with Taylor series expansion around point phi I, we can write like this, and we can check the coefficients of phi I prime, phi I double prime. So, in this case we do not have any phi I term in the left hand side. So, obviously this should be 0, and the coefficient of phi I prime, that should be 1, and again we do not have any second order derivative on the left hand side. So, this will be 0. So, with this information we can construct the linear algebraic equations, and if we solve this we can get the values for the coefficients. So, in this case we have first order derivative with second order discretization. So, let us consider the case for second order derivative. Like find forward difference, we can apply this approximation. So, with forward difference, we can write this again. If we use backward difference for phi I plus 1 and phi I, we can get this approximated form of forward difference. Now, if we check the backward difference approach, again we can start with backward difference and we can get the same expression. So, now if we check the order of accuracy or truncation error for this second order derivative, then we can see that with this Taylor series expansion for phi I plus 1, phi I minus 1, we are getting this truncation error, and this is the order of accuracy for the second order discretization. Now, second order derivative, in previous case we have estimated with a symmetric stencil or arrangement of nodes. In that case, we have considered I minus 1, I plus 1. So, if we apply the same thing here with coefficient approach, then we can write using Taylor series expansion these three expressions. Now, phi I double prime we can write as linear combination. So, we have to remove the phi I and phi I prime del x terms. So, in this case we can write these three equations, and if we solve this, we will get again the approximation in terms of our second order derivative, which is coming similar to or same as our previous expression. Now, one sided 3 point second order derivative. If we consider one sided derivatives, in previous case we have considered symmetric one, I minus 1, I plus 1. In this case, let us consider one sided. That means, first case I minus 2, I minus 3, I minus 1, I, and next case we are getting this order of accuracy, which is del x in this case. So, if we apply the same approach for non-uniform grids, then we can write this as with non-uniform spacing, that means I minus 1 xi del xi. So, with this information, if we expand and utilize the Taylor series expansion, then we can get the desired expression for second order derivative. So, what are the observations? One sided m point stencil provides m minus 1 order accurate first derivative. This is valid for forward difference and backward difference, because I minus 1 or I plus 1 I, in that case we are getting first order accurate scheme, and second case we are getting m minus 2 order accurate for second order case, a second order derivative, and to approximate nth order derivative we need at least n plus 1 neighboring points. And accuracy of the solution of a problem depends on accuracy of discretization of differential equation and accuracy of discretization of boundary condition. Thank you. এই ওখানে দুটো প্রবলেম আছে, দু তিনটে, একটা ডেল এক্স এর পাওয়ার কম নেই, হ্যাঁ না এই যে এইটা, হ্যাঁ এইটা একটা পাওয়ার কমবে, এই দুটো, এটার স্লাইড নম্বরটা টুকে নাও তো, এটা 22, এই 23-এও, হ্যাঁ কোনটা, না না এক্সপ্লেন করছি না, আমাকে একটা স্লাইড চেঞ্জ করতে হবে, এই জায়গায় স্কোয়ারটার বদলে এটা স্কোয়ার থাকবে না, আমি এই স্লাইডটা পাঠিয়ে দেবো, ঠিক আছে, ওটা চেঞ্জ করে দিতে হবে, এটা চেঞ্জ করে দিতে হবে, 22টা 23-এ কিছু নেই, 24-এ অ্যাকুরেট হবে না, সেকেন্ড অর্ডার ডেরিভেটিভ, অ্যাকুরেটের বদলে এখানে ডেরিভেটিভ হবে, এখানে ডেরিভেটিভ, আর এটা হচ্ছে অর্ডার ডেল এক্স, আরেকটা এটা স্কোয়ার হবে 21, আর এখানে একটা স্কোয়ার হবে, তাই না, এটা ডেল এক্স স্কোয়ার দুটো, আরেকটা জায়গায় আছে, আরেকটা হচ্ছে এই স্লাইডটা, এই যে এটা এম না, এটা এন হবে, এটা 1 2 3, এটা একই স্লাইড নম্বর চেঞ্জ হবে না, আমাদের ক্ষেত্রে তিনটে ছবি আছে, এটা এটা স্লাইড নম্বর হবে 8, এইটাই আছে, আর কিছু নেই, আর বাকি সব ঠিক আছে, 21 22 24, একবার দেখে নি, 21 22-এর কাছে এসেই আমার ইয়েটা হলো, ঠিকই আছে, এটার থেকেই হয়েছে, হ্যাঁ এইটা দুটো 21 22, 22-এ এটার পাওয়ারটা কমবে, আর এইটার একটা, ঠিক আছে ডেরিভেটিভ ওটা, হ্যাঁ আমি 4টে স্লাইডই পাঠাবো না।